Alright, lecture 85, simple harmonic motion, pendulums. So we're going to continue our discussion of simple harmonic motion, which we began last time talking about the quintessential simple harmonic motion, which is a mass on a spring. Today we're going to extend that argument, just see that it applies to other systems. In fact, it applies to all kinds of things, big and small, from astronomically sized things like pulsars to teeny tiny things like molecules. Okay? So in general, if you have a potential energy surface, let's just say it's something like this, okay? And you find yourself in some point in here, right? You can always approximate the potential right around this minimum as a parabola, okay? And so as a consequence of that, right, what this says is that you can get simple harmonic motion there. Remember, the parabola was the shape for our potential energy curve for the mass on a spring, right? So it also means that the force is proportional to the displacement, right? Hooke's law, essentially. So basically it says that everything is Hooke's law to a first approximation, as long as you don't get too far away from this point. So in the case of a spring, that means that the oscillations can't be too large, right? You stretch the spring out too far, you know, it's going to be inelastic at that point, okay? So to kind of demonstrate that we can apply this to many, many different things and how it works, right? How do we turn everything into a spring? We're going to talk about a pendulum today. And you're all familiar with a pendulum, right?
Yeah.
Crude pendulum with my fingers and this meter stick, right? Of course, the friction is pretty high because my fingers are not, pretty rough. So, but that's the idea with a pendulum. It's an object suspended from a rigid rod of some sort, fixed at some point such that it's going to swing back and forth as I've drawn here. Okay? And so to break this down, probably the trickiest part to this is finding my pen. Here it is. The trickiest part to this is setting the problem up correctly, right? So let's see how we would do that. So we're going to do Newton's law on this object, right? So I've drawn the kind of the curved path that it's going to fall, right? And we'll call this path length S, right? So we can remember that S will be equal to R, the radius of the circle that this thing is making, but that's the length L of the rod, times theta, the angle that it rotates through, okay? So the distance the full way around, of course, is the circumference of a circle whose radius is L, right, or 2 pi times L, okay? But let's look at the forces that are acting on this. Of course, we have gravity, which is acting like this, right, minus mg, where m is the mass of this object suspended on the rod. We'll assume the rod is of negligible mass, okay? Otherwise, we're talking about what's called a physical pendulum. Physical pendulum is you take some mass distribution. You know, you hang, I don't know, a pillow from a point, and then you give it a push. It's going to oscillate back and forth just like a pendulum does, right? You can treat that as if it was a real pendulum whose center of mass was this mass here, and whose rod length was the distance from the center of mass to the point of rotation. Right? That's physical pendulums. We're not going to talk about those, but anyhow. Okay, are there any other forces acting here? Can you think of one more force maybe that's acting? And we're going to ignore things like air resistance and stuff like that. Well, I mean, it's obviously not accelerating to the ground, right? Why not? What's preventing it from doing that?
A string holding it up.
No, it's not a string, it's a rod, but it could be a string, I suppose. But I said rod. Yeah, we could call it a string or a rope if you want. But yes, there's going to be a tension, T, directed in this direction, right? T, tension. Okay? And so now what we want to do is we want to break down, right? Where is do you see that the distance that the pendulum is traveling is this curved path?
Yeah.
Right? So its x-coordinate, if you will, is really this curved path, S. Okay? So what we want to do is we want to get the direction of the force that's in that direction, right? And that's a tangential component of the force. Remember, since this is a circle, right, the tangent to the circle is always pretty easy to find, right? It's going to be perpendicular to the radial line, okay? So all we have to do is imagine some tangential component of force like this, okay? In this case, at this phase of the pendulum swing, it's pulling this way, right? When it swings over here, it'll be pulling back in the opposite direction, right? It'll always be pulling like this, you see? So reverse direction here, and then back like this again. Can you see that?
Yeah.
Yeah. But there's also this component of the force which is parallel to the tension here. So I'll call this F sub little t for tangent, and we'll call this, well, we don't need to call it anything. We can actually write out what it is, right? Because here is the angle theta, right? If this is the angle theta, this is also the angle theta, right?
Yeah.
You can see that pretty clearly. And this component over here, right, which I probably drew a little too long, do it like this, is actually this arm right here as well. You see that? This vector?
Yeah.
These are the same vectors, just I slid it up here to see that it's acting on this mass, right? So we can write these components down, right? So this is minus mg times the cosine of theta, yes? Let me make a better theta. That's not much better. Whereas this component here, right, f sub t, is equal to minus mg sine of theta. Okay? So that's the components of gravity, right? There's a component that's along the opposite direction of the tension in the line, right?
Yeah.
That's what's keeping it from falling, so to speak. And then you have this other component which is tangential to the curved path that the pendulum is traveling, okay?
Okay.
So now we have everything we need. We can basically write down that the force, at least we're only interested in the tangential force, right? The forces in the direction of the tension, right, are completely canceling, right? This minus mg cosine theta is equal to t. Okay? That's why it's not accelerating, so there's no acceleration there. But there is acceleration in the tangential direction, right? So this will be equal to minus mg sine theta, but it's also equal to mass times acceleration through Newton's second law, right? So this is from Newton's second law, right? Yes? And that gives us the nice consequence that the masses just cancel out, right? So we can write that the acceleration is equal to g times the sine of theta. Okay?
Okay.
So, yeah, there's a sine, it should be minus g. Okay? Now, we're going to make an approximation here. There's a couple of approximations that we'll use in this lesson. One of them is, they're both small angle approximations. One is for the sine of theta, right? And this one is pretty easy to see. The sine of theta is approximately equal to theta if the angle is small, right? And this is really just a consequence of, if we think of some really small angle, right, theta, right, then this component here, which is the sine, right, is approximately the same as, and I'll draw, this is some radius r, right, and we would have a curved arc here, right? So this is the s equals r theta business, right? So this chord is equal to this little section of arc if the angle is really small. If the angle is big, you can see that's not true, right? If I go for a big angle, right, like say over here, right, here's the chord, here's the arc. Obviously not the same, yes?
Yes.
Okay. But if the angle is small, then the chord and the arc are about the same. So that's the small angle approximation for sine. We'll also use later the small angle approximation for cosine, which is not as straightforward to get, but it's basically 1 minus 1/2 theta squared. Let's see, I'd have to think if you can get that any other way than just calculus. I'm trying to think, is there a geometrical argument that I remember off the top of my head? And I cannot think of one, but maybe we'll revisit that some other time. But the small angle approximation for sine is pretty straightforward. We're going to use that now, right? So we're going to say, oh, okay, well, let's just replace sine of theta then with A is equal to minus g theta. Okay?
Okay.
Then I'm going to use this formula, that the arc length is equal to L, the length of the string, or the rod, times theta, right? And I'll solve for theta, and this will give me that A is equal to minus g over L times S. Did I do that right? Theta is S over L. Yes, this looks good. Okay? Make this G. That's fine. Let's recall from yesterday the fundamental equations for simple harmonic motion, right? We had that, so SHM. X is equal to some amplitude times the cosine of omega t plus delta, right? The velocity is equal to minus a omega times the sine of omega t plus delta, and the acceleration was equal to basically minus omega squared times x, right? So this was the fundamental relationship where x is just this again, right? So a cosine omega t plus delta, right?
Yeah.
So let's look at this acceleration, and let's look at this acceleration here. So if this simple harmonic motion, remember that I said that if the force is proportional to the displacement linearly, then you have simple harmonic motion. And when you make the small angle approximation up here in this equation, such that the force is equal to minus mg theta, or minus mg over L times s, the displacement, then we have that. That's the condition that we need for simple harmonic motion. Okay. So now let's see. Compare these two equations, right? The basic equation for simple harmonic motion is acceleration with the acceleration we have here, and you'll notice that omega squared is equal to g over L, right? Because here's our s, which is analogous to our x, right?
Yeah.
Here's our negative sign, so omega squared must be g over L, right?
Yeah.
Now, that's interesting. Yesterday it was, I think, k over m, right? So the frequency, right, how fast it oscillates, was proportional to the spring constant, but inversely proportional to the mass, right? So a smaller mass would be a faster oscillation.
Yes.
Heavier mass would be a slower oscillation. Yeah. Here, there's no mass term in there. This should be a little bit surprising to you, I suppose. If we create a pendulum, right, and we give it some amplitude, right, and release it, it's going to swing, and its frequency, the frequency at which it swings, is not going to be dependent on the mass of the object suspended there. You might think that a heavier mass would go slower or maybe faster, who knows, right? But it's not the case. It doesn't depend on the mass, only the length of the string or the rod, okay?
Okay.
And that's interesting. This is actually a good way to figure out what gravity is, right? Because so we'll write down here that for a pendulum, that's a terrible omega squared is equal to g over L. So if you can accurately measure the frequency, actually there's another term called the period. How do we relate that? So the period T is equal to 2 pi over omega. Why 2 pi? Because we're using radians, right? So we have to divide those out, or multiply those out. But 1 over the frequency. So if something oscillates, for example, say 1 cycle per second, right? Its period, that means how long it takes to go from here back to here again, is 1 second, you see?
Yes.
Remember that the period, when you graph it as a cosine wave, right? From crest to crest, or peak to peak, whatever you want to call it, right? The time that it takes to go from start here and then return here, that's the period. Okay?
Okay.
So, yes, you can easily measure the period of a pendulum. If you were to use a 1 meter pendulum like I had before, the period is going to be on the order of about 2 seconds. Okay? If you use, a quarter of a meter, roughly a little less than a foot, then you'll get a period of a second, and that would have been what they would have used maybe in an old-fashioned clock that used the pendulum as the way to keep time. Okay?
Okay.
Okay, so we've established that the acceleration, right, has the right form. So we can, of course, write down some equations for its motion, right? So you could write that s, right, is going to be equal to the amplitude here will be s naught, right? The distance from, say, this point here where the theta is 0, right? Whatever the distance is on this curved path that you pull it up, right, that will be s naught times the cosine of omega t plus delta again. I'm not going to go through it and derive it for initial velocity and initial position like we did with the mass on the spring, but you can do that, okay? And you get a similar result. The velocity, it's the velocity, the tangential velocity is called v sub t, is going to be, is that right up here? There it is. Be minus s naught times omega times the sine of omega t plus delta. And the acceleration, which again is tangential, right? Should have specified that up here, but it's fine, is minus g over L s naught cosine omega t plus delta. I think that's right. Omega squared, yes. It looks good. Okay, so those, basically it's the same equations we got for the mass on a spring, except this time for the pendulum. One last thing I want to look at regarding the pendulum. I should note that you could, if you wanted to, write this out in terms of theta. That might be preferable. So you're like, well, let me see, what's the initial angle that I rotate this pendulum to, and then release it? Okay, so you could do it in terms of theta if you wanted. Then this would be theta equals theta naught times cosine omega t plus delta. This would be a d theta dt, or delta theta over delta t, right? The change in angle as a function of time, so it's like an angular velocity. And this would be the angular acceleration in terms of theta. should have written this down. Let's just summarize this here. Get my pendulum here, but I'm not interested in the dynamics of the pendulum anymore. This time I'm interested in its energy, right? So I want to know what the potential energy is. And so this we'll call our zero for potential energy, the floor. Okay, remember the potential energy is mgh, the height, where h is some delta y, some altitude, right, that you're considering. So if you choose the floor as 0, then h is just the distance from the floor, right?
Yeah.
And so we want to know, well, how can we write the potential energy for this pendulum? And so if we think about it, right, when the pendulum is at theta equals 0, right, it's of length L, right? So this distance here, from here to here, is just L, okay? Now what about this distance here? It's the same thing as this distance over here. It might be easier to see it here. It's the same though, right? Do something like that. So what is this distance here? Well, it's the same as this. That's just L times the cosine of theta, right? L cosine of theta, okay?
Okay.
Which means that the altitude, this is our h, right? This distance here, which gives us the potential energy for this pendular mass, is just L minus this distance here, L cosine theta. L cosine theta. Which means that the potential energy, U, is equal to, is it minus? Do I use a minus? No. It's equal to mg L 1 minus cosine theta. Okay? Yeah?
Yes.
And this is where we're going to use that small angle approximation I talked about, right? This is the small angle approximation for the cosine, okay? So if I substitute that in here, then we get that this is approximately mg L 1 minus 1 minus a minus is plus 1/2 theta squared. Yes?
Yes.
That is equal to mgl. We've got a 1/2 in front, 1/2 mgl theta squared. We could substitute in the theta using the what do you call it? Arc length formula, I think it's called, which gives us that it's equal to 1/2. We'll get theta is going to be s over L, so we'll have an s squared over L squared. They'll cancel with this L, so we'll get mg over L s squared. And then we can finally, g over L we recognize from here, that's just omega squared, right? So that's 1/2 m omega squared s squared. Okay? Where s is, again, the distance that you travel along this curved path. So this is, again, a parabola, right? If we were to graph that, it's a parabola. And if we were to look at the actual potential energy function, right, using this 1 minus cosine business, right, and compare it with the approximation that we got, it would look something like this. So if I plot this, I'll use weird units. I'll use units of 1/2 m omega squared. So it'll be u over, or maybe 2u over, now we'll leave the 2 out, this makes it confusing. U over m omega squared, okay? And this, of course, is s, right? So we'll get a curve. So here's our parabola. So this is 1 minus cosine theta. And I should have drawn a different color, huh? And the parabola will be ½ s squared, okay? So when the displacement is small, right, it fits the actual potential energy curve for the pendulum, you see?
Yes.
So it's valid within these regions. So what counts as small? Definitely less than 30 degrees. At 30 degrees, you get like a 5% error using the small angle approximation. So if it's 15 degrees, then that's great. That would be fine, okay? The smaller, of course, the better the approximation. But this is an example of how we can take a system and show that approximately, at least for small displacements from equilibrium, simple harmonic motion is displayed. Okay? And that's a commonality throughout the universe. Everything basically is a spring to a first order approximation. Okay?
Okay,
Does that sound reasonable to you?
not really.
Okay. Let's see. I think we'll probably, next time we'll do waves. We'll start on waves, and we'll do a few lectures on waves. They're obviously related to oscillations, because there's, they look like a wave, right? It's just a little bit of a extra bit that we have to take into account there. But so start on waves next time, and then on to thermodynamics. Any questions?
How is everything a string?
Well, because if it's a bound system, right, it's going to have some potential energy function, right, that's going to have a minimum somewhere. If something is sitting still, it's sitting still because it's in some minimum on a potential energy well, right?
Yeah.
And we can always fit a parabola to that. It can be the craziest looking potential in the world, right? Think about we talked about orbits before, right? We talked about the planetary system, and when we take angular momentum into account, right, we get, where r is the distance between the planets, right? We'll have asymptotically approaches zero, so we define the potential to be zero at infinity, right? So it asymptotically goes there, right? This is where the planet normally is, right? It could oscillate between a few points, right? Particularly if it's on an elliptical path, right? That's kind of an oscillation if you think about it. But look at the shape down here, right? Can I not draw a parabola that's going to fit in there nicely? I mean, I can. It says this is an asymmetric potential. It's going to fit one side a little better than the other, but as long as your displacements are small, that parabola is a good approximation. Okay?
All right.
So that's why, because everything that's bound in some way is bound means that it's on a little minimum like this. Yeah?
Yes.
Okay. And that's basically why. Any other questions?
No.
All right. Till next time.